flow theory, and we have done the basic analysis, then the then we did the stochastic analysis for the gap and the flow, and then last time we started with the queuing theory. So with the queuing theory, there are three important things: how is the arrival and the departure of the service, and how many channels we have, and what is the queue discipline. And in traffic, we normally follow FIFO, which is first in, first out. Okay, so the arrival and the service can be deterministic or stochastic. So deterministic, I told you, we mean one value for, so we have one fixed value and other values do not have any chance. When you go for stochastic, then all values have a chance. Okay, the chance can be 0 or 1%, 2%, 3%, whatever, but there is a chance attached to it. Okay, we did a couple of examples for the DD1 case. The first case where the demand and service rate were constants. Okay, the second rate where the demand rate was varying according to time with this equation, and the service rate was constant. Okay, and this is the thing which we did for one of the gates. Now, did anybody try the analysis for the other gate, for the priority pass gate? This example, there were two gates. We did the analysis for one of them. Did someone try for the other gate? Yeah, anyone? You were supposed to repeat this thing for, instead of 20%, 80% of the work, and this will change. This will also change. For the priority pass, it was, I believe, more. I don't remember now. So the priority pass was taking how many? 15 vehicles per minute. Okay, so the thing was you had to repeat this by 80% here and by putting 15 here. So did anybody try it? Okay, very well. Still, it's your task. If you don't do it, it's up to you. Then we have the third case. As I mentioned earlier, in this case, we will be going through examples after examples. There's nothing much to it. Okay. So after observing the arrival and departure rates at a highway toll booth, the toll booth is something which you may have seen on the causeway, where you have to pay before you pass. Okay, so in some countries, in Pakistan and even India and other countries, we have toll booths on our national highways as well, inside the country as well, not only on the border. So on a highway toll booth, they observed the flow coming and going for 60 minutes, and they found that the arrival and departure rate were deterministic, but they were time dependent. So for both of them, they have an equation. Okay, so this is for the arrival rate and this is for the departure rate. Remember rate. So lambda is vehicles per minute and mu is also vehicles per minute. Okay, not number of vehicles. Okay, and you have to find out the total delay at the toll booth and the longest queue. And we are assuming DD1 queuing because this side is deterministic. And we have only one toll booth, so DT1. And now, before we go on to finding out vehicle delay, or let us start. Okay. First of all, we have to find out the time to. We have to also find out the time to dissipate the queue. Okay. which we do by equating the sum of arrival and departure. Okay. Okay. So we have to find out number of vehicles arrived and number of vehicles departed. This is the equation for arrival rate, vehicles per minute. Okay. So how do I find out number of vehicles in this case? Tell me, what should I do to find out number of vehicles? They gave me rate of vehicles. How do I find out number of vehicles? Tell me, what should I do? You can go on and type or open your mic. I can listen to you, and I also hear when you type, when you send me a message on Blackboard, obviously. So what do we do to find out the number of vehicles if we have the rate, the equation for the rate, not the rate, the equation for the rate? What do we do? Yeah, anyone? How do we find out the number of vehicles if the equation for the rate is given? We just did it in the previous example. We have to do the same thing here. What is that? Yes, anyone?
And differentiation.
Not differentiation, we do integration. Okay, we have to integrate. So I have to integrate first of all lambda. Okay, so when I integrate lambda, okay, this will be 2.2 t plus 0.17 t square divided by 2 minus this will become cube divided by 3. Okay, so minus 0.0032 t to the power 3 divided by 3. Okay, so this will give you number of vehicles for number of vehicles which are arriving. For departing, we will integrate this equation. So this is n arriving. I want n departing. I do the integration for mu, which is so 1.2 t, and this will become a square 0.07 t square divided by 2. Okay, for the q, when the q finishes, so I need to find out what was the time of the q. Okay, when did the q finish? So I have to equate them. Okay, so 1.2 t plus 0.07 t square equals this whole thing. Okay, so if I put it equal to 0, then 1.2 t will go here, so it will be only t. Okay, and 0.07 t square upon 2, for the upon 2, right? Yes, upon 2. Okay, 0.07 t square upon 2 will go here, okay, uh, and will be subtracted from this one. So 0.17 minus 0.07, it will be 0.1. 0.1 t square divided by 2, okay, minus this as it is. Okay, so how much is t? Tell me.
16.48.
16.48.
No, 60.
60.48 minutes. Okay, this is correct?
Yes.
Okay. Now at this time, I will calculate how many vehicles arrived. Okay. So I will put 60.48 in this equation. Okay. So this will give you number of vehicles arrived, which is how much now? What is the answer for this one? Yes. How much is this?
143.1.
Okay. So we have 143 vehicles arrived during this time. Okay. Now we have to calculate the total delay for the at the above time. So for the total delay, we will take the integral. Okay, so once again integral. Okay, at this time, uh, not the integral. Just give me 1 second. What are we doing here? Yes, we are taking the uh, so we will take the integral one more time, the difference of the integral, okay, for this time, okay, and we will take the difference of integral for this time, okay, the time which we calculated, okay, and this will give us the, so I have to integrate this one more time, okay, both of them one more time, and put that and I'll put t equal to this one, the one which I calculated, 60.48. Okay, so when I take the integral of this thing, okay, all t's will increase in power, okay, so it will be 2.2 I'm directly doing the integral t square. So instead of t square, I will write 60.48, or for your convenience, let me write the equation first. T square divided by 2 plus 0.17 t cube now here we have the problem. We should have done, so it was already divided by 2. 0.17 was divided by 2. Okay, so 0.17 divided by 2 means how much? 0.17 divided by 2 is how much? How much was 0.17 divided by 2? Tell me. 0.085. Okay, so 0.085, this is t cube divided by 3. Okay, then I have the next one, so 0.0032 divided by 3, how much is this? 0.0032 divided by 3, how much is this? Okay, so plus 0.0010, sorry, 00106, okay, t to the power 4 divided by 4, okay, minus, now I need for this one as well, this one is easier, okay, so 1.2 t square divided by 2, and what is 0.07 divided by 2? I believe it's 0.035. Okay, why minus? Because I am subtracting arrival from, I'm subtracting departure from arrival. Okay, so minus, this equation is in this equation is plus, sorry, not this one, this one, this equation is plus, but I am doing subtraction, that's why. Okay, so 0.035 t to the power cube divided by 3. Okay, so this will be equal to my delay. Okay, and here I'll put t equals 60.48. Okay, so how much is the delay? You replace the t in this equation with 60.48. So how much will be the delay? Okay, so I did the first integral. The equations were given for rate. I did the first integral, it became the equation for number of vehicles. I did the second integral, it became the equation for area under the curve of number of vehicles. Now I'm taking the difference between them to find out the area under the curve, or the difference between the area under the curve. This will give me total delay. Okay, how much is this? If you put t 60.48 here, how much you get? Yes, anyone. How much is the delay here? Total delay. Yes, how much is this? Okay, this is in vehicle minutes. Okay, this is total delay in vehicle minutes. If I want average delay, I will divide by number of vehicles. This value. Okay, so average delay will be total 65474 143.1. Okay, so this will give you average delay. Okay, you can tell me how much is this. Now we want the queue of length at time t. Okay, so we want to know at what time the queue becomes maximum. Okay, we want to know at what time the queue becomes maximum. So okay, so this is your average delay. Okay, this is your average delay. So now the queue was arrival minus departure. Okay, so this is number of vehicles arrived, this is number of vehicles departed. When you take the difference, it becomes the queue. Okay, it becomes the queue. So and when you take the difference, this is the equation you get, right? No, not this one. We did it right for solving. Yeah, this yeah, this one. Okay, so this is the equation for the queue. Okay, this is the equation for the queue, arrivals minus departure. Okay, when we did arrivals minus departure, we got this equation. Okay, we put it equal to 0, so the q equals to 0. Now I want to find out when the q is maximum. Okay, this is the equation for the q. When q reaches maximum, the derivative of this equation will become 0. Okay, when q reaches maximum, the derivative will become 0. So I have to do, so this is the equation for q. So q equals this thing. Okay, when q becomes maximum, then dq upon dt will become 0. Okay, so what is dq upon dt? When I take the derivative, this will become 1, this will become 0.1 upon 2 will be 0.05, 0.05, and instead of and then I will multiply by 2 again, right? Okay, so it was it will become 2t, right? 2 from t square to 2t. Okay, so 0.1 divide by 2 multiply by 2 because of the derivative. Okay, so it will be 0.1 t. Okay, minus same thing here. Okay, it will become 3t, and you are dividing by 3 as well, so this will be gone. Okay, so 0.0032 t square. Okay, so this should be equal to 0. If this is equal to 0, then how much is my t? Okay, so q means arrival minus departure. When I took the first integral, I got arrival and departure, both equations. So I take arrival minus departure, this is my q. So this is the equation of arrival minus departure. Okay, and I take the integral, take the derivative, okay, and put derivative equal to 0. This is the point where q reaches maximum. So this is 38.22 minutes. Okay, very good. So now you put 38.22 in this equation. Okay, so how much is q? Okay, 51.7 beakers. Okay, so the maximum q length is 51.7 or almost 52 beakers. Okay, you have the equation for the rate, you take the integral, you get the number. Okay, and if you want the delay, you will take another integral and take the difference between them. Okay, and when you take the difference of the number, the difference of the first integral, you get the q length. Okay, and if you want the maximum q, then you take the derivative, put it equal to 0, that will give the time when the q is maximum, and so on and so forth. Okay, so we were doing deterministic analysis. All these equations were not giving any chance of any other number, so each equation was giving us one number at a time. Then we move on to stochastic analysis of the q. Stochastic means now you are dealing with chances, so every number has a chance. Okay, so 51.7 had a chance. Okay, even 55 had a chance of being the or what was 51.7, the q length, right? So even 55 has a chance of being the q length. Okay, 51.7 may have a higher chance and 55 may have a lower chance, but in the end, in stochastic analysis, every q number, every length of the q has a chance. Okay, so the analysis which you will be doing, we need to define these five parameters. Okay, like for the deterministic analysis, we need to define whether the arrival is constant or varying, departure is constant or varying, and how many are the number of channels. In this case, there are more parameters for stochastic analysis. First of all, the distribution of arrival and departure. Okay, the distribution can be uniform, it can be Poisson. We already studied Poisson, and I told you this is the most commonly applied to the traffic analysis. Okay, the method of service, FIFO, random. Okay, first come first serve means FIFO. Okay, it is random, it is priority based, or whatever. The characteristic of the length of the queue. Okay, queue length can be finite, queue length can be infinite. Okay, so finite infinite means what? So if you take the example of the one which we did last time with the gate. Okay, so there's the park, and the park has a gate, and the queue is in front of the gate. Okay, now if the queue gets longer, it will go onto the highway, it will start blocking the road. Okay, so the queue can only be up to the edge of the road. If it goes more than that, it will block the road. This is what we don't want. So in that case, the queue length will be finite. Finite up to what? Up to the edge of the road. Okay, infinite means, okay, the queue can be of any length, it will not disturb anybody else. This is what we mean by infinite. Okay, what else? Yeah, distribution of service times. Okay, so in previous examples, the service time, the examples which we did last time, the service times were also uh, you know constant, deterministic. Okay, 15 vehicles per minute, 20 vehicles per minute. Okay, or every vehicle taking 15 seconds, something like this. But the service time can also be stochastically distributed. It may also be following uh, a distribution, Poisson distribution, uniform distribution, something like this. Okay, service time means the departure rate, the departure rate. Okay, so the first assumption was about the arrival, the fourth one is about the departure. So both of them can be stochastic. And then the channel layout. Okay, channel layout I already told you. We can have single channel or multiple channels. In this case, you may have multiple channels which are in parallel or multiple channels which are in series. Okay, so I have multiple channels. For example, if you go to the causeway, you will see both of them. Okay, so you enter the causeway, you have multiple booths on which you can pay. Okay, then you go forward, you will not, you cannot exit the causeway. The next one will be for the passport. Okay, so there is a channel, and then in the same path there is another channel. So this is the channel in series. Okay, channel after another channel. And parallel means there are multiple channels at the same point. Okay, so it can be both, it can be multiple channels. Okay, single channel. And if it is multiple channel, the multiple channel can be in series or in parallel. So series means channel one after the other, and parallel means they are together on the same point. Okay, for this type of analysis, the important point here is the raw factor. Okay, raw means arrival upon departure, the rate of arrival upon departure. We are doing now, we are looking at the equations for single channel. So there's only one channel. We have exponentially distributed demand and uniform service rate. So service rate is deterministic, and the demand arrival rate is stochastic. Okay, M represents what? M represents Markovian. Okay, so here M represents Markovian. So Markovian is another name for exponential distribution or stochastic distribution. Okay, or stochastic distribution follows exponential distribution. Okay, so Markovian demand or arrival, deterministic service, and one channel. Okay, this is how we read this expression. So whenever you have this case, these are the equations you can use. Okay, so raw means arrival upon departure. Okay, rate. Okay, arrival rate upon departure rate. Then this is the average queue length. Okay, average queue length. This is the average waiting time, and this is the average time in the system. So we have average waiting time and average time in the system. Waiting time is when you are waiting in the queue. So how long did you spend in the queue? Time in the system means waiting time plus service. Okay, so T bar is waiting time, which is W bar plus service time. Okay, so the difference between waiting time and the total time in the system is the service time. Okay, so in all these equations you can see we are using the raw factor here. Okay, and the raw factor should be less than 1. The raw factor is less than 1. Okay, so we have less vehicles arriving and more, the arrival rate is less than the departure rate. Arrival rate is less than the departure rate. Okay, this is the condition for these equations. If we do not meet these conditions, then these equations are not used, they cannot be used. Okay, now in stochastic analysis, what we are doing now, there are a lot of variations. Okay, and these equations are derived after some probabilistic analysis. Okay, now this course is not about probability. Okay, so we are not going into the derivations. So we will only discuss the cases for which you already have ready-made equations. Okay, but if you go and do a specialization in this field, You can develop your own equations for other cases as well. So you may have equations in which lambda upon mu is not 1. Okay, so in those cases the equations will change and you can drive your own equation. But this course is obviously not going into the details of these things. Okay, so we are only looking at the cases for which equations are already available. Okay, so we have this example which we solved earlier, recreational park. Okay, now the arrival rate is 180 vehicles per hour and it is Poisson distributed. Okay, Poisson distribution means uh, the interval between the arrivals is following exponential distribution. Okay, so when something follows Poisson distribution, the interval between it follows exponential distribution. what what does it mean? So for example, I have 180 vehicles. Okay, 180 vehicles means one vehicle comes, then after a few seconds another one comes, after a few seconds another one comes. Okay, so the vehicles, their arrival is following the Poisson distribution. So if somebody asks me for the number of vehicles, I will use Poisson distribution. Okay, but if somebody asks me what is the difference of time between the arrival of two vehicles, so when the first vehicle comes, after how many seconds the next vehicle comes? Okay, because the number of vehicles is changing, so the difference of time between them is also changing according to distribution. Okay, and these distributions must be inverse of each other, right? The distribution must be inverse of each other, because uh, if I have, if the number of vehicles increase, then the difference between them is decreasing, right? The time interval between them is decreasing. When number of vehicles, now if it is 180, okay, and goes to 200, so when it was 180, the time interval between them was x. When it goes to 200, the time interval between them will be decreased, it will be less than x. Okay, so when number of vehicles are increasing, the time interval decreases. So when number of vehicles are following Poisson distribution, the time interval between them is following exponential distribution, and these two are like inverse of each other. Okay, they are inverse of each other. Okay, the park starts at 8 a.m., closes at dusk. Okay, whatever the dusk is, darkness, the start time, and we have to calculate the average length of the queue. Okay, average waiting time in the queue and average time spent in the queue. Okay, MD1 case, this case. Okay, what was the service rate? The service rate, every vehicle was taking 15 seconds. Okay, every vehicle was taking 15 seconds. So if you want to calculate per minute, we did it earlier as well. It was 60 seconds divided by 15. 60 seconds in 1 minute and 15 seconds per minute. Oh, sorry, 15 seconds per vehicle. So this will give us vehicles per minute. So we had 4 vehicles per minute. Okay, I just want to. Okay. So we have the service rate was every vehicle takes 15 seconds, okay, to go from the gate. So in 1 minute we can have 4 vehicles. 60 seconds divided by 15 seconds per vehicle. Okay, so we have 4 vehicles per minute of service rate. Okay, so first thing is I will calculate the raw factor. So raw is arrival upon departure. Okay, so arrival is I need to convert the arrival into per minute as well. Okay, arrival is 180 per hour. Okay, so per minute is how much now? 180 divided by 60. How much is per minute here? 3. Okay, So the raw factor is arrival upon departure. 3 is the arrival rate and 4 is the departure rate. 3 upon 4, how much? 0.75. Okay, so that means I can use these equations now. Okay, I can use the equations which are given in this case. Okay, so you are only using raw here. So give me these values: Q bar, W bar, T bar. Okay, 0.75. Raw is 0.75 in all the cases. Okay, so 1.125 vehicles in the Q. Okay, next one, W. So you need mu here. Okay, mu is departure, 4 vehicles per minute. Okay, mu here is departure, which is 4 per minute. Okay, W is 0.375 minutes. Okay, so on average every vehicle waits for 0.375 in the queue. And how much time average for the system T? Okay, so I told you the difference between these two is basically uh, the service time. Okay, so this is only for the queue and this is queue plus service. Okay, so thank you so much, Zainab. We can move on. uh, Anybody has any questions? Is everything clear? Okay, moving on. We have the case for MM1 now, and again we have undersaturated infinite queues. So queue length is not a problem. Undersaturated means that the arrival is less, the departure is more. Okay, if you have arrival equal to departure, it becomes saturated. Okay, when arrival equals to departure, it's saturated. When arrival is more, departure is less, it is oversaturated. Okay, so undersaturated means arrival is less, departure is more. Okay, so in this case we are using small q for the arrival and big Q for the departure service. Okay, small q arrival and big Q for the service or departure rate. Now we have MM1 case here. Okay, so what was the meaning of M? Can someone tell me? What was the meaning of M? M stands for what? Yes. In this notation, M stands for what? Anyone? Okay. You need to go back and check what M means. Basically,
Markovian, doctor.
yes, Markovian. Yes, thank you. So M means Markovian. So I will read this that I have Markovian arrival Markovian service and one channel. Markovian meaning is stochastic, so it follows probability distribution. Okay, so small q is following probability, big Q is also following probability. Okay, so probability of having n units in the system. Okay, so probability of having two vehicles in the system. Now system includes two things. System means q plus the service channel. Okay, system comprises of two things, the queue and the service channel. Okay, so probability of having n vehicles in the system means that probability of having n vehicles in the queue plus the service booth, whatever you have. Okay, so this is the equation you have. Expected number of units in the system. Okay, expected number of units. Expected means, in simple words, mean number of units in the system. So P of n will give you the probability of having any number. This is telling you most probably what number you can expect in the system. So here I can put n equals to 0, n equals to 1, 2, 3, any value. Okay, but and each number will have a probability, will have a p value. Okay, so 0 may have very low probability, 1 may have some probability, 2 may have high probability, 5 may have very low probability, whatever. But which one is the most expected number? So that is en. Okay, so en is the most expected number you can have in your system. Okay, most expected number. Okay, then the most expected number in the queue. So this is for the system and this is for the queue. And now I told you the example between the system and the queue. System includes queue and the channel itself. So this is without the channel, bidun channel, and only the queue. And if you want to calculate the average queue time, average queue length, this is the equation. If you want to calculate the average waiting time, there is the equation. And if you want to calculate the average time in the system, this is the equation. Okay, so these equations work where you have these conditions met, m1. Okay, and here we are still using the Poisson distribution. So service and arrival both are following Poisson distribution, keep it in mind. Okay, you want to calculate average waiting time in the queue, average waiting time of an arrival. Okay, including the queue and service. Okay, so expected, wherever they are using e something here, they mean the average or the mean. Okay, expected, the mean according to probability means the mean value. The expected value according to probability means the mean value. Okay, because mean is something which you are most commonly expecting. Okay, when we calculate the mean, we have it in our mind that this is the value which will be most common in the group. Okay, so that's why we call it the expected value as well. Okay, then the equation for spending time less than t in the system, then the probability of waiting for time less than t in the system, and the probability of having more than n vehicles in the system. Okay, so this equation was having n vehicles in the system. This is having more than capital N vehicles in the system. Okay, so this is for a fixed number. This one is for a fixed number. So n can be 1. So probability of having one vehicle in the system. Here, capital N, let's say capital N is 1. Okay, so this will give you probability for 2 and 3 and 4 and 5 and 6 and all the way up to infinity. Okay, so this one is not for a single value. This one is not for a single value. It is for all the values which are more than capital N. Okay, so this is the difference between them. Okay, on a given day 425 vehicles arrive. per hour at a toll booth located at the end of a off-ramp rural expressway. Okay, toll booth I already explained with the example of causeway. Vehicles can be serviced the single channel, and the service rate is 625. Okay, and now we will assume that both of them are stochastic, probabilistic. Okay, so we have to calculate the percentage of time when the toll booth will be free. Okay, uh, now uh, arrival rate is small q, departure rate is the large q. Okay, so small q is 425 vehicles per hour, and the large q is 625. Okay, so you can see the service rate is higher, the arrival is lower, so this is undersaturated. This is undersaturated, so again you need to meet the conditions. Okay, this is for undersaturated conditions. If they are not undersaturated, these equations will not work, or you should not use them. Okay, so percentage of time when the operator of the toll booth is free. When he will be free? When there are no vehicles in the system. Okay, when there are no vehicles in the system. So when basically n is 0. Okay, when n is 0. So you have to give me the probability when n is 0. How much is that? This thing is 400 something, this thing is 600 something. I already gave you the values in the chat. So how much is p of 0? I need p of 0. How much is that? So this is power of to the power n. Okay, so you will put it this equal to 0, this whole thing will become 1. So you just need to do 1 minus small q upon big Q. How much is that? 32. Okay, 32%. So 32% of the time the operator will be free. 0.32 means 32%. Okay, average number of vehicles in the system, which is this one. Okay, so how much is the average number of vehicles in the system? Tell me. Okay, so almost 2 vehicles on average will be in the system. Okay, average waiting time for the vehicles that are waiting. Okay, so these are the assumptions for these equations. Okay, so we don't have to worry about them. We are assuming Poisson arrival and negative exponential distribution for service time. Service time is the difference between them, right? So I told you when we have Poisson for the number of vehicles, we have exponential for the time between the vehicles. Okay, so these are complementary to each other. So average waiting time for the vehicles. Average waiting time. Where is average waiting time? This value. This is the average waiting time. Average waiting time is W bar. W bar. So how much is that? Average waiting time. Okay, so average waiting time is 0.005. Now this is in hours because we kept everything in hours, right? Per hour. So if you convert it to minutes, how many? How many minutes? 0.3 minutes, which is very, very low. Okay. Then we have single channel undersaturated finite queues. So the last one was infinite queue. So the queue length can be anything, but here we are putting a limitation on the length of the queue. Okay. Raw means the same thing, arrival upon departure. We already used it. Okay. small q upon big Q, arrival upon departure, probability of having any number of units in the system, expected number of units in the system. Okay, and this is the question we have. So we have only two things here. Okay, number of vehicles entering on the ramp of an expressway by a metering system that allows the maximum 10 vehicles. Metering system is like a signal. So signal opens only for that much time in which 10 vehicles can come onto the freeway. So in the whole hour or whatever time you have, in one time when the signal opens, it will allow 10 vehicles to enter on the system, enter into the highway. Okay, so this is called a metering system. When a signal is installed on the ramp, okay, and that signal is only allowing a fixed number of vehicles to enter the freeway from the ramp, we call it a meter, ramp meter. Okay, so it's a signal which has a fixed number of vehicles to be allowed. So it is allowing 10 vehicles per minute. Okay, so if the vehicles can enter the expressway at 500 vehicles per hour, so this is their arrival. They can enter, so this is their departure service rate. So they can enter the freeway at 500 vehicles per hour, but they are arriving at 400 vehicles per hour. So departure is higher, arrival is lower, undersaturated. Okay, we have to find out the probability of 5 cars on the ramp, percentage of time the ramp is full. Okay, the ramp can maximum have 10 vehicles. The ramp can maximum have 10 vehicles. Okay, so we have to calculate the percentage of time when the ramp is full, meaning when there are 10 vehicles in the system. Okay, and here the system, there is no booth here. So system is the queue itself. Okay, we are talking about a highway, so there's no booth here. So there's no service time here when you are in the queue or you're not in the queue. Okay, so the queue is a system now, and the expected number of vehicles on the ramp during the peak hour. Okay, so my small queue is 400 vehicles per hour, my big queue is 500 vehicles per hour. How much will be my row? 400 divided by 500. How much is that? 0.8. Okay. Okay, so this is my raw value, probability of 5 cars. So I need P of 5. Second thing, percentage of time the ramp is full. Ramp is full means 10 cars. So P of 10, and then I need the expected number. Okay, so give me these values, P of 0, P of 5, P of 10, and then this value, expected number of vehicles. Let me check the time. Okay, we are over the time, so you can calculate these factors yourself. Okay, I leave it up to you.